My name is Jim Olson, and I'm excited to tell you about what I'm calling the numeric, geometric, and algebraic trifecta. This is a really cool form of mathematical reasoning that's going to help you in many, many ways in the future. And it's a nice little problem that is accessible to middle school students, but can also be a challenge for high school and college students. At the end of the video, I'll give you a little bit of background and theory, but let's get into it. This is the basic idea of what we're going to be doing. We're going to be having a geometric pattern with steps, a numeric pattern, and a resulting algebraic pattern. In this particular geometric pattern, we have 3 stars, then 5 stars, then 7 stars, and we can anticipate what the next step might be. Excuse me. Step 4 is going to be 9 stars. Our algebraic expression is 1 plus 2n. And we're going to see that the 1 has meaning in our geometric pattern, our 2 has meaning, and our n has meaning. Many of the patterns I'm going to be using are from a wonderful website called visualpatterns.org, where there are hundreds of patterns to investigate. Let's take a quick peek at the website. This is the Visual Patterns website. And what you do is you click on one of the patterns, it shows you the first few, and then it says that step 43 is going to have 173 in it. And this is a challenge for you to figure out how they got the number of squares in the 43rd step. Now I'd like to do some specific examples. And in each case, we're going to do 4 things. We're going to figure out how many spots or X's or figures there are in the 4th pattern, the 4th step, the 5th step, the 10th step, and the nth step. We're going to write a general algebraic expression. So in our first example here, in the first figure, we have 4 dots. In the second figure, we have 8. In the third figure, we have 12. For n equals 4, if we think about what this is going to look like, we're going to have 4 dots on each side, and there are 4 sides. So that means our number is 16. For n equals 5, you might think about what the number of spots is going to be. That's going to be 20. Now, we've got lots of nice patterns going on here. Numerically, it certainly looks like we're adding 4, but the question is why? Well, there's a couple of reasons. One explanation is that we have 4 sides in our figure, and each time we're adding 1 spot. Another way to think about this is to break it up into parts. Thinking about sticks, we have a stick here at the top. That's a group. We have a stick here. We have a stick here. And we have a stick here. We have 4 sticks of length 3 in the third figure and 4 sticks of length 4 in the fourth figure. So for n equals 10, we're going to have 4 sticks of length 10, which is 40. And now for step n, we're going to have 4 sticks of length n. There's our algebraic expression. Now let's go to example 2. Okay, so let me change my color here real quick. This is step 1, this is step 2, this is step 3, step 4. I need to find step 5, step 10, and step N, because that's what the directions were. So this is the step number, and this is the number of squares. And we can just count them up. We get 4, 7. You might go ahead and count them on your own. Maybe pause the video and see if you can fill in this table. 10, 13. And I can see numerically that I'm adding 3, but we shouldn't just blindly figure out that we're adding 3. We need to have a reason. Now, when we look at our diagrams here, we have a certain portion that is staying the same every time, and we have portions that are growing. I'm going to highlight the portion that's staying the same. This yellow square in the center is the one that's staying the same. In the second figure, it's this yellow square. Third figure, fourth figure. So I always have that center point that is not changing. And then my sticks are growing. So it looks like in this particular case, I have 3 sticks. So the fifth figure is going to have a single dot, which is 1, and it's going to have 3 sticks of length 5. 1 plus 3 times 5 is 16. In the case of 10, we're going to have a single dot plus 3 sticks of length 10, which is 31. Now, the sticks aren't always of length n, but they have been of length n in my first 2 examples. Now pause the video and see if you can write the general expression for step n. The general expression for step n is 1 plus 3n. 1 because of the one single square, 3 because we have 3 sticks, and n is because each stick is length 3. Now let's move to example 3. Once again, we're going to make a table for ourselves. Here's step 1, step 2, step 3, step 4. I need to figure out step 5, step 10, and step 11. Step N. This is the step number or the pattern number, and this is the number of flowers. And you might count these up and figure out if you can figure out a way to count them. Now, once we get to the third figure here, I don't think it's a good idea to just count 1, 2, 3, 4, 5, 6, 7, 8, 9. You want to think about this and count it multiplicatively. I have a rectangle here that's 3 by 6. 3 times 6 is 18, plus 2 sitting to the side makes 20. In the fourth figure, I have another rectangle. It's 4 by 8, which is 32, plus 2 sitting next to it is 34. So this was 4 times 8 plus 2. So what I'm thinking about here is the constant 2, and I think I'm highlight this again in yellow. This constant 2 flowers stays the same every time. And then I have a rectangle. And the rectangle in the fourth case is 4 by 8. In the third case, it's 3 by 6. So let's see what the number is going to be for step 5. Step 5 is going to have a rectangle that's 5 wide times 10 high plus 2. That's 52. The 10th figure is going to be 10 wide times 20 high plus 2, which is 202. And now pause the video to see if you can figure out what the expression will be for the nth step. Well, we're going to have a rectangle, and the width of the rectangle is n. The height of the rectangle is 2n. And then we have the 2 flowers next to it. So we're going to have n times 2n plus 2. N times 2n plus 2 is our formula. Now, it might be interesting to simplify that a little bit and think about that. I might do that later on in the video. But for right now, I think I like leaving it that way because n has meaning. It's the width of my rectangle. 2n is my height of my rectangle. And then 2 is my constant 2. The fourth example is going to be a little bit different. In our fourth example, we have 1 spot, 8 spots, 27 spots. You might pause the video and see if you can see what the pattern is. This second figure has 2 groups of 4, 2 squares. The third figure has 3 squares, 3 groups of 3 squared. Notice that a square is a square. The next figure is going to have 4 groups of 4 squared, which is 64. The fifth step is going to be 5 groups of 5 squared. Five to the 5th power is going to be 3,125. In the 10th figure, we're going to have 10 to the 10th, so maybe we'll just leave it as 10 to the 10th, which would be a 1 with 10 zeros. And in the nth figure, we're going to have n to the nth power. This is a little bit different example and not super common, but kind of a nice example to think about. This type of reasoning of connecting number patterns, geometric patterns, and algebraic formulas is very important mathematical reasoning. Pam Harris has a nice website, and on it she created an excellent graphic that shows the flow of mathematical reasoning from preschool all the way up through high school. We start with counting, then we think about additive reasoning, then multiplicative reasoning, which moves into proportional reasoning, and ultimately functional reasoning. One of the nice things that's also nice about this figure is that she has spatial reasoning. This bar connects all the way back here to preschool and kindergarten. Spatial reasoning is important all the way through. What we're doing here is working up in this area here of thinking multiplicatively and moving into functional reasoning. These algebraic expressions we've been writing are actually function expressions. Okay, I'd like to give you an inside tip here on finding these expressions. If we have one-dimensional growth, in other words, sticks that are growing, just getting longer or shorter, this is going to result in a linear expression, which means the expression is just going to be x to the first power. Now, it might be, for example, 4x or 4n, like we saw in our first example. Furthermore, if we have two-dimensional growth, in other words, regions that are growing in both width and length, this is going to result in a quadratic expression. Expressions using x squared, that is, x to the second power. So, in the first example, we have these sticks getting longer. This is one-dimensional growth. We have n to the first power, 4n. In our second example, we also had sticks getting longer. We happen to have 3 of them. Our expression was 1 plus 3n. This is linear, first degree. The 1 is the constant 1. In the third example, our formula was n times 2n plus 2. So n times 2n, that's 2n squared. That's my quadratic term because these regions here are getting both wider and taller. I would like to look at this expression just a little bit more. Here we have our pattern and our data, and we determined that the expression for the nth step is n times 2n plus 2. If we take n times 2n, we get 2n squared. And this is our quadratic term here, indicating that it's growing in 2 dimensions. But I might maybe put parentheses around the n squared for emphasis here. So apparently I have 2 squares. Let's see if we can explain why. Yes, in fact, we have a square right here that's 4 by 4. And we have an identical square above it that's also 4 by 4. So we have 2 times 4 squared, and then we have our plus 2. Back here, we also have 2 times 3 squared plus 2. Back here, we have 2 squares and our constant 2. And even in the small little first diagram, I have 2 squares. They happen to be trivial squares, but I have 2 squares plus 2. The interesting thing about these visual patterns is oftentimes students will come up with different expressions. But if we take a look at the expressions, they're usually equivalent. And each expression can be explained in their own way. It is important to be able to connect the algebraic formula to both the numeric pattern and the geometric pattern. It's also important to know why it works. Each character in the algebraic formula should have a meaning in the geometric pattern. In this video, we have shown how to connect geometric patterns, numeric patterns, and algebraic expressions. Down in the notes for the video, I will include a couple of other handouts, visual patterns practice problems, and visual patterns homework. I hope you found this video interesting. Have a great day.